Now in this example, you'll note that if I had these two forces here pulling outwards, it acts like a single force, which is called the resultant force. So I'll show you what that looks like again. So in our example before, we had it where we had a force like this, which was 5 kilonewtons and 30 degrees from the horizontal. And we had another force, and this one was 4 kilonewtons at 30 degrees this way. Now, as you can tell, if this was a person standing here and I had two ropes pulling me, that person would probably be yanked in a certain direction, and that's called the resultant force. And we worked out by mathematics on the previous one that the resultant force was 4.58 kilonewtons at 79 degrees. So that's about the same as, so this person would go in the direction of this arrow with a force, so this is the resultant force of resultant is equal to 4.58 kilonewtons at 79.1 degrees. Alright, so that person will be pulled in that direction. Now, what would I have to do to make it so that this person is not pulled by anyone, wouldn't go in any direction? So what kind of opposite force would be required to keep this pole or this person still? So that's called bringing it into equilibrium. So right now, these force vectors, the sum of their forces in the x direction is not zero, and the sum of the forces in the y direction is also not zero, because it's pulling the person in that direction. So one of the laws of equilibrium states that the sum of the forces in the x direction must equal zero, and the sum of the forces in the y direction must equal zero for something to stay still or be with no net forces. It's not going anywhere. So what kind of extra force do we have to add in to make sure this pole or this person stands still? Well, you'd probably guess that the force would be most likely something like this. You have to have another force pulling you in this direction, and that would obviously balance it all out, except there's no net force. So this one would be called the equilibrant. So how do we find out, how do we calculate this one? Well, let's make a little chart. So our very first force, we'll call this one force 1. This is force 2. So we found out that force 1, the magnitude of that force was 5 kilonewtons, and we divided it up to figure out its components, looking at the previous example. So we can find that here's our components. So we had the x component was 4.33, and the y component was 2.5 kilonewtons. Okay, and force 2, that one had the components that look like this. So force 2 was a 4 kilonewton force, and the x component was negative 3.46, and the y component was 2 kilonewtons. Alright, now the equilibrant force, so the force we need to find out in order to keep this in static equilibrium, or so that there's no net forces happening, we'll call that Fe. Alright, and we need to figure out what that is. So what we can do is we can add up all the forces. So the sum of the forces in the x direction must equal 0 for it to be still or in equilibrium. So let's add up all the forces. So we have 4.33, take 3.46, so I'm going to add these two, plus Fx. Okay, now you see that you got one variable, so let's solve for that one. So we have 0 is equal to, and I'm going to add them two together in my calculator. Okay, and now if I solve for this, if I put that to the other side, I get Fx is equal to negative 0.87 kilonewtons. Alright, so that's my equilibrant force in the x direction. Let's now solve for the force in the y direction. And it must be equal to 0 for it to be in equilibrium. So let's add up these ones. We get 2.5 kilonewtons plus 2 kilonewtons plus force in the y direction. Okay, let's resolve this. So 0 is equal to 4.5 kilonewtons plus force in the y direction. Okay, so force in the y direction is equal to negative 4.5 kilonewtons. So we've just figured out what this equilibriant is. So if I was to look at it, it is definitely, so let's look at this. In the x direction, it goes to the left, 0.87, so just a little bit. Okay, and then it goes down, 4.5. So you can see I've guessed it pretty good. How do we solve for the actual single force? Well, we have to plug that into our very next equation. So let's try this next one. So the force is equal to Fx squared plus Fy squared. Okay, so let's solve for that. X was negative 0.87 squared plus negative 4.5 kilonewtons squared. Now anytime you square root a negative number, you'll find that it becomes a positive number. So we get a force of 4.58 kilonewtons. Okay, and our angle is equal to the inverse tangent of Fy over Fx. So let's plug that in. Fy was negative 4.5 kilonewtons over negative 0.87 kilonewtons. Now here's one major thing you need to consider. The force and the angle are all in positive numbers. So you might think initially, I need to draw my equilibriant up here. But that's a mistake. When you do this through this method, you actually loses the negatives. So it does kind of trick you. If you look at the components, you'll find that it actually should be in the negative x region and in the negative y region. So these things are still correct, but they're just not giving you the indication of where to draw it in the graph. So the true answer for this, the equilibriant, is actually in the negative, so this is the negative x and the negative y region. So we're going to go negative 79 degrees, so that's from this direction, 79 degrees. And the magnitude is 4.58. As you can see, it's the dead opposite of the resultant. So that's how you can figure out your resultant and your equilibriant. So to find the equilibriant, once again, you make a chart of forces, you add up all the individual component forces, you add in the equilibriant force, and then you solve for Fx and Fy of the equilibriant force. Then you move down and you find the single force and the angle.